¿Qué tal? Muy buenas tardes a todos.
Good afternoon, everyone. Welcome, both to new faces who've just joined us now and to those who are here to the bitter end. This is going to be the last session for the day today, and we're going to be hearing to Santiago. But before I introduce you to him, let me just remind you that you can participate on Twitter with our hashtag. We encourage you to share pictures, comments, content, whatever. So, let me give you a little bit of background for the next session. We have more and more threats to information security, and this struggle makes it very clear that we need to further protect our data as much as possible. Handling information can be enhanced through machine learning, and we're going to be hearing from Santiago Hernandez Ramos about how to do so effectively. Santiago is Senior Security Analyst at CyberSoc at Deloitte. He has a master's and a PhD on information science at the University of Zaragoza. I'm sure that you will make the most of this workshop, this session. And welcome, Santiago. The floor is all yours. I hope you can hear me okay. Let me thank you for joining me at this workshop. I want to thank the organizers for inviting me back once again. So let's start with the title as such, which is Machine Learning, Our New Ally for Information Security. Is this a true statement? Well, not quite, I say. What is not quite right? Well, the fact that machine learning is not quite a new ally. It hasn't come up or popped up in the last couple of years. It was there, but because in the past we couldn't capture information or process it as fast as we can now, well, it hadn't boomed the way it has more recently. This is a table of contents for my presentation. I hope you can see it okay from the back. We'll do our best. So, I will start telling you about the current situation on cybersecurity connected with artificial intelligence. And what is machine learning? It's a buzzword or a buzz expression. We'll see what applications are possible right now. We'll see something about linear regression. Or linear, sorry, regression. We will see how algorithms can learn. Well, I don't know if learning is a word. I think that is a buzzword in that case. And then more advanced techniques like classification, clustering, anomaly detection, and then very simple techniques that you can probably use for basic security in any company. I don't think we need this information because I've already been introduced to you before starting. So let's see the current situation. What is our starting point for cybersecurity here and now? Very briefly, at least, I would like to stress a number of points. For instance, even though in the last few years there seem to be many more cyber attacks, more companies impacted and at a larger scale, that's what we hear. But in fact, threats have not changed that much in the last few years. So that's good news, right, for us to detect them. It is true that they're more large scale, more people and more companies are impacted, but still, malware, ransomware, different types are the same, very much the same or very similar at least. I also wanted to tell you that the fact that we have more cyber attacks or more larger scale cyber attacks led by maybe mafias, shall we call them, rather than by loners. Well, as Charlie Miller says, behind and over and above all of this, what is at the end of it? What is it? Well, is the bottom line is money. It's economy that matters. Miller said that there is a strong evidence that the best researchers in cybersecurity are now motivated more by monetary gain than by prestige. That is, how much money can I make out of this particular vulnerability? That's why we have mafias that buy vulnerabilities, they launch them large scale, and they make good money from doing so. So, before we start talking about machine learning, I would like to tell you a little bit about artificial intelligence. What is the difference between AI and ML, sorry? Well, they're connected, but they're not the same. This is a report from the American government. We see two quotes from 2018, from this year, how artificial intelligence is changing the American lifestyle. Thanks to that, we can now diagnose pathologies better, finance work better, transport and mobility has been enhanced. For instance, we have autonomous vehicles to prove it. That's the first quote up on the screen. And that very report also said experts forecast that rapid process in the field of specialized artificial intelligence will continue. But we don't think that in the coming 20 years cognitive capacity for AI will be the same as human cognitive capabilities. So that means that artificial intelligence is improving many processes, but we should still have our feet on the ground and understand that artificial intelligence is well below human cognitive skills and capabilities. Not now, and it won't be in the coming 20 years, probably. Certain tasks will improve, and some might even exceed human capabilities, but not for the global number of tasks. So, artificial intelligence and cybersecurity. This is nothing new. This is not a new field. And no matter how some people are still reluctant when they hear about machine learning, we have to acknowledge it is used here and now, although not for global complete solutions, but in traditional cybersecurity processes, we can get a part of it and replace it by machine learning with a final global improvement of the process. An American report said the following: today's AI has important applications in cybersecurity, and it is expected that it will play increasingly a role both in defensive and offensive cyber measures. That means that in the coming years, the offensive role will also be present. Not just defensively, but offensively, attackers using artificial intelligence and machine learning to develop new, more harmful attacks. I haven't seen a lot of literature connected with offensive cybersecurity paired up with AI and ML, but that's certainly a field of research for future papers. So, now let's see the connection between AI and ML. Well, more and more in recent years, successful applications of artificial intelligence, most of the time they're using machine learning or some sub-disciplines within machine learning. That means that machine learning is part of artificial intelligence. So, which part of artificial intelligence does it equate to? Well, not all artificial intelligence issues can be solved through machine learning. Why? Because for machine learning, we need data. That subset of artificial intelligence, machine learning, what it does is uses statistics and processing, but always on data. It needs data. What is machine learning, in fact? Well, this is probably the most common definition for machine learning. We see it up on the screen. Machine learning is a subset within artificial intelligence that helps systems learn and improve automatically on the basis of experience without having to be programmed to do so. It's based on different hypotheses underlying the model, and it tries to improve it, adjusting with more data within the model over time. The most important part of that definition has to do with the fact that we're working with mathematics and data, but then we can infer certain features that will help us make decisions in the future, make forecasts, and all of this, importantly, without teaching the system or programming it to make those predictions and forecasts. So, we now know what machine learning is, although some of this is quite complex, on adjusting the model or the parameters of the model. We will see more about that shortly. And then what types of machine learning do we have? One of them would be supervised learning. We'll see later how we define learning, but let's just remember that one of the subsets within machine learning is supervised learning. That is machine learning where there's a mapping between input and output based on pairs. That means that we have a set of data where we have an input value, output value. We give that to the algorithm. We then give the algorithm an input value, and it will automatically come up with the output value for us. We'll see more details about that later. And then supervised learning is divided into two different types: classification and regression. What's the difference between them? An algorithm using supervised learning and using classification, it means it tries to predict or forecast discrete values. That means they're clearly limited. For instance, is an email spam or not? That type of classification. Whereas in regression, the prediction is, or attempted prediction, is for continuous values or neighboring values. For instance, how much does this house cost? Well, I tell the algorithm that it's a 3-bedroomed house, and then it can predict or forecast the cost. Let's see now more about regression within supervised machine learning. Let me give you an example. We want to predict the cost in euros of handling an insurance claim, depending on the system or the equipment that's been affected. For instance, in a security auditing, we find a security failure that involves 100 different PCs within a company. Well, how can we calculate and forecast what cost would be involved in an attack to that system? We need to start by finding other security incidents that happened in the past, see how much those cost, and check up against the number of PCs were involved. Then on a graph, how would that look? Well, something like this. This dot here is an incident where 50 PCs were impacted and the cost was 100,000 euros. This is another case with a cost. This is just a way to portray the data in a more graphic manner with that line. So the machine learning algorithm basically builds a model for prediction. Look at this very simple example where the model seems to fit quite well like so. That line would join the dots on the incident that we've had in the past, and that line would tell us what the trend is. So let's predict how much a security incident would cost where 75 PCs were involved. I have the input variable there, 75 PCs, and that's the result, 175,000 euros. That would be the predicted cost. This is linear regression, where that straight line is the function for that forecast, for that prediction. What about supervised learning, in this case focusing on classification, as opposed to regression? In this case, we're predicting a discrete value. Is this particular email spam or not? In this case, how am I going to predict it? Depending on the spelling mistakes, the number of spelling mistakes, and the number of the exclamation marks on that particular email. Why? Because spam tends to have those too, right? So in a small subset of emails, I study and see which ones were actually spam or not, and count the number of spelling mistakes and the number of exclamation marks on real emails, right? Well, this is just a very tiny example with a very small subset. Look at this email, for instance, with 4 spelling mistakes, 6 exclamation marks, and it was spam. How do we know? Well, because we've classified it. We know it's not a prediction. Well, our function could then predict it like so. This would be the function where a particular email has to be checked for those 2 elements. So if it's on the left of the function, it would be a legit email, whereas if it falls on the right-hand side, it would be classified as spam. Simple example. Another important area for machine learning is non-supervised learning. In supervised learning, the idea was that we had a set of pairs for inputs and outputs, that is, PCs affected and costs involved. Right. What about non-supervised learning? Well, it would be machine learning where a function would be predicted with data that have not been tagged, that is, not classified or categorized. That means that we don't have the output value. Let's go back to the spam example. We have a set of emails. We don't know if they're spam or not. We categorize them for exclamation marks and spelling mistakes, and we had the line or function. So that information was given to the machine learning algorithm as to what happened in real life, so that it could then predict it. Not in this case. It's non-supervised, so the algorithm doesn't know which emails are spam or not. We just give it the data and the set of emails. In non-supervised learning, machine learning, we would end up with a structure that makes sense. Let's look at this situation. A logical grouping would be ending up with these 2 clusters. Can you see how the points there, the dots, kind of cluster up together in one area, and the same for the other subset. That would be non-supervised learning, machine learning. So let's go more in depth now for linear regression, for us to understand how learning takes place. Don't panic. This is quite a common graph. For instance, Coursera uses it for their machine learning courses. This is a new way to define supervised machine learning. In this case, we see that we have the training data sets that are fed to the learning algorithm. As a result of that, the algorithm creates a function that we label as a hypothesis or hypothetic function based on previous incidents. So after that, we can have an input variable, the number of PCs that were affected, and then the function would decide on the forecast or the prediction based on the training examples. Let's go back to the idea of costs after a security incident. How would a linear regression algorithm work with this totally made-up set of data? With a number of PCs that were affected, the cost in €1,000 after a number of incidents where we had those problems in whatever company or in a number of companies. So this table is exactly the same here. It's just that on the right we had a graphic representation. Any idea what this means? This is the function for a line on a graph, straight line. The machine learning algorithm then is fed the input data, and then on the basis of that, it adjusts a function so predictions can be made. So let's start with a very simple function, right? The straight line, something that we learned back in primary school. Let's start by replacing with random parameters. The function has two different parameters, the slope and the point where it crisscrosses. For that linear function. So this is the graphic representation. We've been plotting here. The same. It is the same function. So if I showed you this and the number table, and I asked you how does this represent the trend? Is it a good representation or not? Well, you would have no idea, right? Whereas if you look at it like this, you get a much better idea, because our subset of data looks like it had a different trend. Well, the machine learning algorithm starts like this. It generates a line that doesn't stick to reality, and then the error is calculated. What does that mean? Well, the algorithm gets information from previous incidents. It then portrays them on the graph, and then where we knew both the input variable and the output variable, well, that helps us calculate the error through an error function. Well, mathematically that works. But you can also use an optimization function. What does that mean? That parameters are moved and changed so that the error can be minimized. How? Well, for instance, if I move it this way, it looks like the error margin is lower. Well, it does so as much as possible until the error can't be reduced or limited any further. Well, that would be a pretty good representation of our data subset until the error has been minimized as much as possible. Why? Because it's a straight line on the graph, but it's not quite straight on reality, right? So now we can see how algorithms learn in machine learning, quite simply by getting a particular function, in our case, the linear function, then seeing which parameters are important for that model or function. And once that is ready, then it tries to calculate the error present in our training data subset and try and optimize it until error is at a minimum. And that would mean the function would be good for predicting on that particular data set. It's more simple than you thought it might be, right? For algorithm learning. So once the error has been minimized for the model parameters, then we could get the function. We could forget about the data we had. We would just keep the function. That means we would keep the model that's been generated and then use it to predict new situations. For instance, when somebody asks, how much would it cost if there was a security incident and 100 PCs were affected? Well, we could then go to our hypothetical function. The X would be the number of PCs affected or impacted. And then let me remind you that the model was used just to get these parameters here. Once we've got them, then the training of the algorithm is over. The prediction would be reliable for the subset that we used for algorithm training. So that's the most simple side of machine learning, how algorithms work, how supervised learning gets the data, both input and output, whereas non-supervised learning doesn't get the output variables. Now we are ready to talk about classification, which is the part of supervised learning where we want to predict discrete examples, if an email is spam or not.
So we see linear regression that help predict continuous values such as the cost of a security incident. Incidents is this an example I gave you. We could also use it to forecast how many phishing emails or spam emails will be received at a given organization for a month. We can even forecast within a company which one would get most of the spam emails. So the classification here, if you check it out and you think it through, this would be our daily activity as professionals in cybersecurity. For example, for every email that we receive, an analyst can see whether it is phishing or it is not. For every file on the network, whether it has malware or not. Also any query for a command and control. And these are all predictions, discrete predictions of forecasts. Is it a command and control? Yes or not? Is a bank transfer? Yes or no? These requests, is it a DOS attack? Yes or no? So, we also need to consider when we talk about classification is the fact that many companies nowadays gather data such as logs and events, and processing all this data and the search for requests for threats can be done in a way that is not machine learning. The fact that we are using data to predict whether an email is spam or not doesn't mean that we're using machine learning. If we use it to see whether a URL is malware or not, does not mean that this is machine learning. What about brute force on an attacks on our site? In our organization, as analysts, we check the server, those force brute attacks, and when we see 10 requests from the same IP, it's probably that. So we create heuristics and we say that if there is more than 10 requests, it's brute forcing, and so you block it out. This would be a way to attack or block it based on data from the logs generated, and this is not actually machine learning. So where would we start thinking that something is machine learning? From the previous example, as you can see, we might say, okay, how come we've decided that 10 was the optimal number? Why a minute of time? This is done based on the analyst's experience. Over 10 requests in 1 minute as brute forcing. For machine learning, that subjectivity does not exist. Machine learning is using algorithms processing the data history, as I said before, inferring optimal classification standards following mathematical principles. So the difference between this and this here, we're contributing that part of subjectivity by the analyst, but with machine learning, what we are doing actually is that every parameter up there are inferred by the algorithm through a series of mathematical principles. And here, let me show to you this exercise and how we can use this very simple algorithm we've seen, which is a classification algorithm, logistic regression for spam detection. Here, for detecting spam, I'll use a set of data, which is Trick 7. You can download it from the internet, which was collected in 2007. A series of real emails, if I'm not mistaken, it's 75,000, and that are made public so that the spam detection is improved. We gather all these emails, and if you see, wait for it. This is raw emails that you have run and return, and everything that an email has if it is new instead of how it is rendered by the email client. What's the problem now? Problem is that we have a set of data that is a bunch of emails, 75,000, but in there, well, they are raw, and we have all the headlines, we have HTML, also numbers and characters. An automated algorithm would get a set of data that were numbers that were then processed, and there would be an equation. So we need some pre-processing so that we can get all those emails and turn them into a rendering that is the right one for our machine learning algorithm to build the equation. So one of the first things to be done when we use machine learning is to have the pre-processing on our set of data. If we're using it on real examples, odds are that our set of data that we gather do not show like a table. This is the feature and these are the numbers. If we use it to detect network abnormalities or anomalies, we will have lots of gigas. And if we use it for URLs to download malware, probably we will have a data set with 500,000 URLs, and we say once we have it, what do we do with it? How do we feed them into the algorithm? That's pre-processing. So we will get this, we will send the emails, And we will take out several things. We will remove the headlines. So far we are not interested. We will just keep the body of the email. If there is tags or HTMLs, we will strip it and we will just keep what's inside of it, whatever is going to be rendered. And once we have it all, we'll be using we'll use a given equation or function, getting the whole text string, vector, turn it into a vector so that all those words are represented as a number. And once we have the number, we will send it to our machine learning algorithm that will get the parameters as using the logistic regression, which is a simple equation, same as with linear equation. It would calculate the model parameters, and with that we will build the function we saw before. And as we send the same email parsed the same way, that is spam or it is not. So if we were to run this software, first thing it would parse emails one by one till it's done it all. On the one side, stripping every HTML and headlines, and once it's done, that would be it. It's not the headlines but the headers, sorry. So this is what we have once it's over. So this is the algorithm. Here we see again linear regression, and we see how the code works. But it's trained the algorithm. There's been a forecast or prediction, and it said that for a set of data that had not been classified previously, even though we had classified them to see whether it was good prediction, so we had our set of data for training, another separate set. We've said, well, this is also labeled and I know whether it's a spam or not, leave it here. So once I've trained my algorithm and calculated the parameters and I have the function and the model, I will get that set standing there. I'll send emails and then I'll see whether they are properly classified. So after having trained our algorithm in a logistic regression, very simple algorithm, and having tried our set of data, we have a 99% classification, right? As part of those set of data that were several thousand emails, they were properly classified at a 99% probability. So that's good. I just referred to how this works, but I have not gone deeper into explaining the code. Let me explain something that is way simpler. Let me show the set of data first. First one was a real set of data, real emails, where probably you saw the potential. And here you have a set of data that I've built myself. I've made it up, trying to represent the example we saw before for linear regression. Here we have a set of data which is CSV, a column with the number of devices affected, and the next one is cost of the security incidents. How do we program an algorithm for machine learning to build it, to build a function? You see, with the existing libraries, with Python, this is simply straightforward, and you can do it just like this. This is how we build a linear regression model as the one we see in the previous example that would be adjusted. First, we import two libraries that are very well known in the field of machine learning. Panda, which is a library to manage sets of data. This is a silly one because we only have a few examples. I would say 20 or 30. For the emails, there's worth 75,000 there. We need a library where we can process all those data and do so efficiently. If instead of 75,000 it's 1 million, what we need is something that is truly efficient. We can not just build a loop to go through the file one by one because it would take days. Once we've imported both libraries, only thing we do is we read our set of data. Here is data.csv, and usually this is a data frame. That's the name it's given. Once imported the set of data, you see pandas can read the CSV format right away, and it's turned into an object of its own. And so we gather our input variables. So we stripped it out of the failure cost, just the number of devices. And then we also keep the output variable. Once we have both things, we split the set of data. And why is that? Why do we split it? Well, we do so in order to do what we did before. We have a set of data, and with that we will build our model. But once built, how do we know that it's properly built and not just in any way? Since we have a set of data for which we know what the right answers are, we're gonna split it and leave part of the data to verify that that model has been rightly done with the other half of the set of data. Usually, it would be 20%, 30%, 33% for testing, and the other percentages for training of algorithms. Here you see this is X-text and E-text for testing, and X-training and E-training what I will use for training. How do you train an algorithm? With one of these libraries is very simple. We just import the algorithm. This is linear regression, as you see here, and we've said it so. And with the fit method, we train the algorithm. What does it need to be trained? Easy peasy. Our training data and the responses as well to calculate the mistake and adjust the straight line. We feed both things, and once we've done it, we can start predicting. What's generated here, basically, this is a model, right? Same as saying here, I need the function. This is the linear function. Down here, the parameters, as we've seen, based on what I feed you for training. And once you've adjusted the parameters, I have the object here with the function and the parameters already adjusted with this model. I feed what I want to predict, and you see what I'm feeding is just X-test. So only the first column. So that's the number of devices impacted. And the ePredict is the reply, the second column, the cost it would have for every device based on the training. Once we have that, what we do is, well, here, I just got on the screen the prediction and what's real. So what really was as our set of data and what was predicted. What do we use here? And we've seen that. These are metrics. These are metrics that are used to assess how our models behave, how it's been built. There are so many metrics. Accuracy and precision, F1 score, many of them. When we check the clustering, we will see we have silhouette coefficient and many others used to assess different what the results been. One might measure the false positive to true positive ratio, some others the false positive rate, etc. So, if we run this algorithm, very fast. Why is this one so fast and the other one so slow? Because I had to parse the emails and I had to train it using so many examples, training examples, 75,000, which are not as many. But here we had a bunch. See that the prediction of the forecast, when I split it into 20%, we only got these examples here. It is just 1, 2, 3, 4. So we had few training examples, and if we compared the forecast with reality, we might see that it's not properly adjusted. It's not a proper match. For reality, we had 227. That because of the first incidence, as we predicted using number of machines, is over 100,000, then over 10,000. The prediction was 60,000, 65, 55,000. So it seems that the ratio is preserved, but it's not properly well fine-tuned. It was not the right one. And why is that? Well, it happened because we only had a few training examples. Actually, so few that we only had 2 points placed in a random way. And with the straight line, we cannot really see what's the trend of our set of data. If we did have some more spots or points that would truly represent the relationship between the number of devices and the cost, we could have a much more accurate prediction. Okay then. Next topic, a bit more advanced, clustering. Clustering takes us back to the relationship or how we understand clustering examples in our daily life as cybersecurity analysts. On paper, why would we use clustering, or why an analyst would use clustering? Malicious activity oftentimes happens with groups or sets. See this example here? If an attacker tries to gain access to your network, they will need to scan and have traffic with similar features. So try to come in, so recognition of the network, and so some network scans that had produced high traffic, TCP or whatever, but it is pretty similar. So malicious activity happened within a set of data that are very similar. Then if an attacker tries to exploit an SQL injection, they will try several similar sequences before they find the right one, such as the name of the table or the parameters that are the right ones. If an attacker performs force brute-in, they will be trying several of them. Brute forcing, that is, several of them. So probably they send similar phishing emails to many employees. This happens with sets. And that's clustering for security. Clustering is just another kind of algorithm for machine learning, which is based on unsupervised learning. Here, our set of data, we will have so many data. We don't know whether they're good or bad because we have not classified them before. What's the goal here? So if we have a large amount of data, so let's say that we have a large amount of logs, and we'll be using a clustering algorithm to bring together all those data and logs into groups that follow similar features, and when looking into them, we can start somewhere and it is easier. As we think that malicious activity happens as part of a group or in groups, probably one of those small clusters of our millions of logs, we will have some logs that are part of a malicious activity. So if we are developing a threat hunting, we are a threat hunting team for a company, and we're trying to check threats in the company without knowing what we're looking for, and we have millions of logs to look into, a good starting point would be clustering techniques, as we will see in a minute. So here you have it. The idea is to have the grouping of data, as I said before, and something important here. Once we say these data are grouped, we need to see how to group them. This would be through the proximity concept. And I refer to proximity here, but you might say, okay, proximity, but what do you mean? How do I know that this URL is closer to this one? Doesn't make sense, does it? So this is measured with metrics. Metrics would be a specific way we use to assess the proximity between points or spots. Let's see this basic example, something we can see in our daily life, but it's not considered machine learning in our definition. We would choose one or several dimensions and define every cluster as a group of elements that share values in those dimensions. When you hear dimensions, what we are saying is columns. In the past, before, we had only 2 dimensions in our set of data, so we can represent it there. We had the number of devices and the cost of the incident. That's easy to represent, but usually our set of data will not have 2, but many more, 10, 20, 30. This cannot be represented graphically. So we can use a clustering technique which says 2 dimensions. So, okay? One is the number of devices and then, or endpoints, and then everything else. Value shared are a group. This would be just a basic example of what's used by the SQL example or group. Let's move on to more advanced cases. This is the first machine learning or clustering algorithm. probably one of the most popular algorithms, which is K-means. K-means have several features. The metrics to measure distance. This is about measuring proximity between points and bringing them together so they are the closest. So understand that scenario or premise that it all happens in groups. So proximity concept is measured with that instance, with the Euclidean instance. The great feature here is that it's easily scalable to larger groups. So it's an algorithm that is used for production settings because of that, because we have millions of data, and maybe other advanced algorithms are not so useful for scalability reasons. But then there are some other considerations we need to consider, and I'll refer to that. And how does K-means work? K-means works as it follows. There's something that we will call centroids, which are points we will set into our map randomly. Do remember that, as we said, that there is a table and a graphic representation, same here. So this would be our set of data. We have a table, and we will randomly initialize some of this data. We will decide how many there'll be. All of this, once initialized and once they're inside of our set of data, we might say that they will be assigned data or that are closest to them. We started there, and the closest are allocated. This is all on the blue because they are closer there. Once all those points have been assigned to the centroids that we've looked into, we'll calculate the distance of every spot and take the average and move it as close as we can and back again to the beginning. So we move our centroid. So first it's all on one, then we calculate the average, and then back to the average for everything. Then some here, and then to the middle or the average again. And then we stop moving that around when we see that they are not moving anymore. When it comes at that point where they don't move anymore, we think that every of those has reached a state where every point that have been assigned to them are part of a cluster. And you see that there. All of them combined are a cluster because we've moved the average around those centroids. So what is to be considered when we're using this algorithm? I meant to share this with you, but I wanted to make it clear. So the analysts need to know beforehand the number of clusters, since it is us who indicate the number of clusters need to be initialized and will be moved around. Beforehand, we need to state the number of clusters. What's the problem here? Well, if we're looking into a set of data such as logs, in a search for security threats, and we truly don't know how many clusters are in there, it is difficult to say, well, I'll initialize how many, 3, 4, I don't know how many are there. And if we had a set of tag data, or we knew what we're looking for and the results we're looking for, we can choose 1 to 3 times the number of tags we have. If we have a set of data where we say, well, inside of this, I know there is 1 million items, but there are 3 threads in it, we would get those tags there, all those, and say initialize 1 to 3 clusters, right? 3 times the number of threads. Here it would be 3 to 6 or 9 as well. And we use them and see how they group together, and then we check the clusters. Then we also need to use streamlining or standardization. This is a bit more advanced, but if we refer to standardization, scalability has to be used if we have a set of data that are out of balance. So we get several dimensions as part of our set of data, and there's a first line where the values oscillate from 1 to 5, and the second one has values, and they are fed values from 1 to 2 million, maybe, because 1 here would be the number of rooms, that's one of the features in a home. The other one, the price of the home, or anything of that kind. So there are features inside those sets of data that are out of balance. This is Euclidean distance, as I said. And if they are so wide apart, it doesn't work. So we need to follow standardization mechanisms which keep the data trend, but somehow equalizes every features so that they have similar values. What else? We cannot use k-means with categorical data or one-hot encoding either. If we have one of our features which is not a number, but categorical number, so a category, if something is good or bad, we cannot fit it into the algorithm because it only understands numbers. One-hot encoding, it would say the bad one is a 0 and the good one is a 1. These are very low numbers, by the way, or similar values, so it doesn't really work. K-means doesn't work with sets that have several dimensions, number of rooms, etc. So picture this case. Machine learning on network traffic. We can get so many features out of this package. We can see number of incoming bytes or number of the package. We get that, and we can get the number of bytes through the float, incoming, outgoing, TCP, UDP, and so on and so forth.
If we have many columns, that algorithm won't be working properly. We would be needing dimension reduction algorithms. I'm not going to go into detail because those are more advanced. So k-means works better if the centroids are randomized. In most implementations, they're initialized randomly, and very importantly, k-means takes it for granted that they're spherical. Look at this example. Look at those clusters, how they look like circles, right? When I say spherical, I'm talking about a graphic representation. So that is an assumption, and when they're not spherical, then this technique for k-means grouping or clustering, it just won't be working properly. Let's look at a different type of clustering, because clustering is quite generic. It's based on proximity, and k-means uses Euclidean distance, but there are other possible distances if we have problems with that. In this case, we're going to look at dbScan, a clustering algorithm that doesn't use Euclidean density, but actually it works really well with non-spherical distributions. Let's see how the algorithm works for dbScan. Here we have 4 clusters, and we can see this round cluster that has been colored in red, but we have 3 more smaller clusters with Euclidean distance, centroids, and k-means. Well, if we start to assign values and it all moves to the center, the outer cluster won't be detected. Why? Why not? Because it's not a circuit that's particularly spherical. dbScan works differently because we have to indicate first an epsilon parameter. That would mean it's like a radius around which it looks for neighboring values. So we would initialize a point on our data set. We just get 1 of those points, and we search within that radius. So if it has 4 mean points or over that number neighboring points, that will be a core point as the start of a cluster, and that is done again for other neighboring points. If there are 4 of them, again, we go on and on until the point comes when no more neighboring values are found. So we then look for points that have not been added to that cluster, and we start again. We initialize a different point. This one, for instance, it doesn't have 4 points, so that is an anomaly. Again, here we see that it's got the number of neighboring values that we defined, and recurrently doing so until we find no more, and then we would move onto a different point. We see then density for clustering to be able to cluster points, even if they're not spherical. DB-scan doesn't work properly when we have different densities, logically. Then the selection of epsilon and mean point parameters are the basis for correct functioning of this model. The radius and the number of neighboring values that define a cluster, that's what we need. We don't need to define the clusters beforehand, but we do need to define those parameters. So that will be the basis for the algorithm to work properly or not. It doesn't work properly when we have many different dimensions for that type of data set. And before I show you an example, I want to warn you that you need to be very careful not to alter the density if the set is subdivided into subsets. We have our data set. We need to check how the algorithm works. So that means we need to leave some data for supervision or monitoring without a tag, or at least the algorithm doesn't need the tag for clustering classifications in this case. But we could have the tag and then feed both the data and the tag, and then on testing during that phase we could check to see how the classification into clusters went, to see if all malicious examples went into a cluster and the legit into a different cluster, or if they're mixed together. So if we in those cases, we need to be very careful, again, not to alter the density of the data set. Because if we split them randomly, we might end up with data that are very good representations for some of those data, but not for the rest. Why? Because we altered the density, and that would be wrong. Let's look at a practical case. An example that is a little bit like threat hunting. In a company, a team working on threat hunting. What is the normal cycle then? Well, starting with a hypothesis of what we're looking for, or presupposing that attacks will be of a certain type, and see how it works with certain data sets. We then collect the data that we think will be interesting for the attacking techniques, for us to explore that, and then we start discovering the TTPs. Sometimes data sets are huge with so many different inputs, and where can we start? Well, that's where clustering is useful. If malicious activities happen with clustering, we can start analyzing smaller groups or clusters to see how the activity works there. Let's have a look then at the example.
El ejemplo que tengo planteado es el siguiente.
Here is our example. I start with a set of URLs, legit URLs, and then a set of URLs that are used for malware distribution. Overall, it's about 500,000 URLs. Which ones belong to malware distribution, which ones are legit. That's the exercise. The threat hunting exercise might be caused because some devices have been infected and we want to find which malware have been used. Imagine 500,000 pieces of information. Where can we start? Well, if there has been classification, the clustering algorithm won't see this URL. This has been tagged so that once I have my clusters, I can get the tags and show you which URLs are malicious in a cluster, which legit URLs are in a different cluster. Does this work properly or not? Very importantly, we have the pre-processing step. Here we have our URL set with text, characters, numbers, and with the same problem we saw earlier. The machine learning algorithm gets numerical information, but what we have is text chains. So we can't just feed that and expect a perfect URL clustering. How can we turn the URLs into numerical information representing legit URLs and malware URLs? We need to do pre-processing of our data set and get certain features that we call dimensions. Those are the different columns. Look at the ones I've extracted. Firstly, entropy. What is entropy? Fanon's entropy says the following. Well, it finds the amount of information on a text chain. Which premise can I use? Well, this is my own idea. Extracting the entropy from the URL, and that will finally give me a number. That's the idea. So the premise is the following. When we have normal behavior on a website, on a domain, by a user, the idea is that the user will be browsing from one area to the other. For instance, opening YouTube videos. What would change? Just some numbers, right? Because information is quite similar for those URLs. When we calculate entropy, we see how that result is then clustered quite nicely for legit URL. But when we access a malware URL and we download a doc file, whatever, containing malware, we would click and we would end up on a weird URL with a very long address, with a lot of numbers, with very little information. And the entropy is quite weird, right? There might be some legit ones that would read like that as well, but very few. This could be a good start for classification as a feature to measure distance. What else can I use? TLB. Or TLD, sorry, to see if it's part of a malware TLD set. So I would have my column with TLD malware, and that would score as 0, otherwise it would score as 1. I would also extract the type of resource that is accessed with numerical coding. I would see if it's an IP address or a domain. Because sometimes when we download malware, it's an IP because they haven't even got their own domain. So with the data, I would then need to make it readable by pandas or by CSV in this case. Look at this here. This is a way to justify to you here what I explained earlier. The functions I defined are applied on the URL set with the apply panda function. I'm not a developer, right? I work with cybersecurity, but the first thing that came to mind is that I have defined my functions. I could have my loop, for loop, so that I can extract the entropy of the function, the entropy of the URL, and so on. Well, when I did it, I estimated 13 days to cover those 500,000 URLs. But using Panda, it took how long? 4 minutes for the 500,000 URLs. Can you see how having good frameworks for data processing, loading, for a large data set, like 500,000, right, which is not the biggest we can come across at all. This is the script that we use on our URLs. And this is the result, this data set. Just see how the data set now looks much better it looks much more numerical, still some categorical data that we will later work with, not hot encoding because k-means doesn't work with that very well. And also we're including URLs here. Why? Because when I process with the algorithm, I won't be classifying only the clusters with numerical values. On top of that, I will then have the URL on the corresponding cluster, so that URLs will be in different files belonging to different clusters, and I can then analyze that. Let's have a look at the file in charge of that analysis. It's the same thing we saw for linear regression, the same frameworks I used earlier. This is our new URL dataset that we calculated earlier. We use get dummies, which is a Panda resource for binary encoding. We have loaded some variables that we're not interested in, so I'm going to do a drop of the URL, the entropy, no, not the entropy. I'm going to leave that out. And the label. So for the URL and the label, so that the data set can understand it. It can't understand the URLs, right? And then we will leave the label out later, because if it's a malicious URL, because it's non-supervised learning, they don't need the label. It just works with the structure. So we do reprocessing. We've done scaling before, because some entropies stand at 4 point something, 6 point something. Then we have the encoding with values of round about 1. So there's quite a difference, right? The scaling will help equalize that, because we're using k-means, and it might work wrong when the data set is not properly balanced. So once that's ready, all we do is we instance k-means. Very simple. Look at that. We need to indicate the number of clusters. I'm trying to differentiate between legit and malicious URLs. I have between 1 and 3 times the number of URLs. That's reasonable. So I'm going to say that's 4 clusters. So once we have the number of clusters, here we do feed predict. That means we don't need to feed the labels, just the data set. And then that will contain the clusters and the examples. The loop then gets the URLs into the right cluster, and we end up with the files. And this is the metrics. And that's a bit weird. What are we measuring at the end of the day? We're not measuring probability of it being right or not. We're measuring how well the clusters are defined. That is, containing as many instances of a particular type and as few instances of a different type. So that's where we use purity score, getting both clusters that have been predicted and also real labels. That's why I have my labels to check if the clustering is correct. There's another type of metrics that I can show you in a minute. That's the silhouette coefficient, to see if clusters have been found correctly on the basis of some mathematical properties. And it doesn't even need the labels for the clusters to know if they've been described or found properly or not. If we have time later, we will see how this compares with labels in one case, without in a separate example, and the final outcome is pretty similar. We're going to run the scripts now. Here it is. And look how it predicts. K-means is often used in production environments because it's ever so fast. This is how long it took for 500,000 URLs. This is the classification. It says there is a cluster with 2,708 instances where over 2,000 are malicious. As an amazing classification. Most of the examples are malicious. Then we have 379,000 URLs where 34,000 are malicious URLs that have been included. This is with simple parameters, right? The only complex one is entropy. The rest of the parameters are very simple. And then two more clusters. One with 640 instances where 628 are URLs for malware to be downloaded. And then another cluster with over 6,000 URLs with, again, most of them being malware. Excellent classification. Where we have less data, we would find URLs with common features that have been used to download malware. And all of this on a real data set. The purity score is 0.9%, logically so. And this one is 34,000, but as opposed to almost 400,000 original ones. Here we have our clusters. Let's open dataset 0 that had some 2,000 malware URLs. These are URLs that have been used at different times for malware distribution. They all have IP addresses as domains. Look at the resources that are accessed. I'm going to show you now a different one. Another cluster, cluster number 2. How was that grouped together? Well, look at that. URLs that were distributed for malware distribution. This is the indicator. The real data set, well, it has the number for every instance. Kansas City Hotel, .exe for some of them, or .zip. That might not look very obvious, right? Probably because of the domain. So the algorithm was fed some parameters, and it then uses a function, just like we saw for linear regression earlier. Well, not the same one, but in a similar operation mode. It adjusts parameters, it clusters URLs together, and with a brute force attack, you don't need to say, well, over 10 predictions that will be considered as brute force. No, it just needs mathematical calculations. So that's it for clustering. And now let's see something, well, the last section in my presentation that's very popular in cybersecurity, and it's anomaly detection. I'm going to start talking about intrusion detection, which falls into two different categories. When we find an intrusion, it can be based on heuristics, that type of rule that most companies use. It finds false positives, but it doesn't work very well for unknown or totally new attacks. Through heuristics, rules help this happen. And then there's a different way of doing this based on anomalies, profiling, normal behavior in a system. Could be a website, a host, whatever. And it can find new attacks because it can assess events that deviate from the norm. That is anomaly evaluation or assessment. So when we talk about anomaly detection, we need to first define what an anomaly is. It's an event that deviates from normal or expected behavior, expected from a security perspective. Because anomalies don't just have to do with security. Sometimes they have to do with performance problems. For instance, we have an IHDS finding anomalies on a host, for instance. A system might have a huge load because we're rendering a video. Well, that's an anomaly compared with normal behavior for the processor, not caused, in this case, by a security breach. How did anomaly detection start? Well, to detect intrusions proposed in 1976 by Dorothy Dennings in her famous paper. People are still saying this is new, but back in the day, this paper proposed anomaly detection for this very purpose. So, how is machine learning connected with anomaly detection? Here we have the definition in English, and it says that a machine learning algorithm attempts to recognize complex patterns in existing data sets to help make intelligent decisions or predictions when the pattern deviates from the norm, and what it does is finding non-trivial methods to find them. So this is a new category of machine learning, that is semi-supervised learning, because some algorithms will be completely, fully non-supervised, but some of them need at least your set of legit data, not labeled with legit or malicious examples, but a set of legit examples. The system profiles a function, and whenever there is an outlier, then that will be studied as a possible security breach. So it's semi-supervised because the supervised system needs both legit and malicious examples from the real world. The non-supervised examples doesn't need either of them. We don't need to differentiate between them. And in this semi-supervised learning, it needs to know at least some of the legit examples are legitimate. The most simple example is Gaussian distribution, which is a probability distribution for continuous variables. Here we can see the density graph representing a Gaussian distribution. Gaussian distribution says the following. Don't panic when you see that formula. It says for this particular point, if I get an example there, probability will be far higher than if I get a point here at this end of the curve. So if our data are distributed according to Gaussian distribution, then we will adjust parameters just like the linear function we saw earlier. But in this case, parameters depend on variance, the metrics, and typical distribution. So let's do something similar now, but starting with legit examples, drawing the curve, the function, then adjusting the parameters, and then this function, this will then give back a probability. We would then set a threshold, a limit, so that when there's a new example, it will be assessed according to Gaussian distribution, according to the model that I've described and adjusted for my data set. And if the probability is too low or under my threshold, then it will be an anomaly. But if it's within the limit or larger than the threshold, it will be considered as a normal example. So if the threshold is here to the left, if most data are to the right, then the ones to the left will be unusual or non-typical. So malicious behavior, the idea is that is normally quite different from legitimate behavior. I bet you've often seen situations where you have the logs of our Apache server, for instance, and we try to detect SQL injections. And normally, when that happens, the requests are well defined. For instance, with the same reserved words, quite predictable. But in an attack, SQL injections are longer. They might use unions. They might add other requests for the database, or using reserved words that are often not used. So logically, if we have profiled our normal requests, then we will easily find anomalies, and that will tell us something odd or nasty is happening. How does the algorithm work with Gaussian distribution? We would select characteristics or features that can determine an example or define it as anomalous. Then we would adjust the parameters for the model. Well, the algorithm would do that. And then, given an example, we would compute the probability. If it's below epsilon, our threshold, then it will be classed as an anomaly. Let's see a practical example for anomaly detection, applied in this case to banking frauds with credit cards. This is the normal flow when we pay with a credit card. Well, this is how I've imagined it. I don't really know all the details. We pay with a card for authorization, then the merchant bank is involved, the issuer approves the payment, and then the reverse route until the payment is confirmed. Well, we can use the anomaly detection algorithm where? Here, at this point. With an anomaly detection algorithm, if the transaction is classed as anomalous on the basis of the transactions that individual normally makes, then it has a high probability of being malicious or a fraud.
Voy a utilizar este conjunto de datos.
I'm going to use this set of data. This set of data here is real. We got several features of a transaction using a credit card. This was published by a company, but mainly those are numbers very close together. And why is that? And how can that up there we have V6 and V7? Because they follow a dimensionality reduction algorithm, which is PCA. PCA gets our data set and builds the main components. And with those, it produces the same columns that we had with the same data. And the trend is somehow kept, but different values which are escalated, standardized. And the data set is anonymized, because if it weren't anonymous, we could not get the data, because those are private data. But once anonymized, we have all these transactions classified as 0 legit, 1 malicious. We will not be using malicious transactions, but it's still good to see the result. Actually, this is an easy classification for a bank, because if a client comes and is not complaining, it is legit. And if it claims that they've been stolen or they've been robbed, first thing they do is call and say someone's bought something with my credit card, and so you can classify it as a fraud, and then you use it for training your own algorithm. Let me show you what should be done. What about Gaussian distribution? We said that one of the premises is that our data set has to be distributed according to a Gaussian distribution, which is a Gauss bell shape. It's Gauss bell because the density distribution, as represented, shows like a bell. And what we also said is that for it to work, we need to use features where the malicious examples are different from the legit ones. To the naked eye, this is good when we see the data, but when we have PC8 and everything has been anonymized, to the naked eye it's a bit more difficult. Usually we graphically represent the distribution of data. Here I've represented each of the feature. Orange, you see the examples for that malicious feature, and in blue that would be legit. So I see what feature follows the Gaussian distribution, almost all of them, and we also see, or I also see, which of these features are more differentiating between a positive or a negative example. Here the negative examples are very different, but this one here is almost the same. This would be a poor feature to use for an anomaly detection. These would be a poor one, this one would be quite good. With this here, what I do is, okay, I will keep those that I know are good because they are differentiated and follow a Gaussian distribution. All others will be removed from the data set, and so I train my algorithm. Okay. But so that you'd see that this is the Gaussian distribution that has not been implemented as a machine learning, and so you need to implement it yourselves, but it's pretty simple. Actually, if you want to test it, just email me and I will send it to you. But we do what we saw from previous examples, so let's run it. This is something I haven't told you, since I need to have a threshold, a limit, above which I would think it's an anomaly, but I don't really know what the limit is here. So what I do is I try different limits. I get my data set and split into two or three, and one of them I use this for testing. So this is for casting. I see the labels, I see if they match a malicious example, and I say yes, it's a match here. So this is a good threshold. No, there's too much a difference. This is a bad one. So I keep the best one. Since the data set, I've been using it for limit selection. I cannot use it afterwards for testing. And why is that? Because it might be there's been what's known as overtraining, which means that the limit is nicely adjusted to the subset of data, but not for the generic subset. And so I get just the same set for the limit or threshold and the same one for testing. So it's a good test because it's been selected for it, but when deployed real time, nothing is detected. And that's why it is important that when any of the parameters are gathered like that, you need to use a different subset for testing afterwards when you're going to assess it. Final result, if you check it out, you will see that it got it actually detected the anomalies with an 80+% accuracy. Not so bad, is it? So these are legit transactions that belong to a real bank, and 82% of all cases. So many, because there's been thousands and thousands of transactions. It's been a match. And the anomaly was actually a perfect match for fraud or legitimacy. So if it's a fraud or malicious, we can follow other techniques we've seen before for supervised learning that helps us truly verify that it is a fraud and reduce the number of false positives, not so many here. And so the last algorithm I got you here, we have 25 minutes left for questions. So this is for anomaly detection, and contrary to Gaussian detection, does not need to have the legit or the label data set for profiling. Here we have an algorithm which is for trees, following two premises here. The abnormal subset, it's a minority to cope through the regular data, and the features are very different from normal data. Before I show you in a graph how it works and see the practical example that I have for this network attack detection, let me tell you that this algorithm is very good when you want to use it for network traffic abnormalities real time or for detection processes with a high load. Why is that? Because it only uses a few training data for good results, and even if we use a very large set, there is a subsample with just 1-2 examples, and with one example it can decide which ones are abnormal and which ones are not. So it's very fast, and it needs not many data, and doesn't need labels because it's unsupervised, so it's good for real-time deployment and in order to have the real-time processing within reasonable deadlines. How does it work? First, the graphic representation, how it works, and you can find on any site or anything doing with isolation forest, and then shortly I'll explain what this is all about. Let's say we have this data set. We have two features and it shows like that on our table, and we see human being is quite good at spotting abnormalities in sets and everything, and we see there's a large group. This one could be thought of as an abnormality, and up there probably it is compared to our data set. So what about isolation forest? First, horizontal and vertical cuts or slices. So we split it here, then this one here, then this one here. Right here it would be done as a function. Isolation forest counts the number of lines, vertical and horizontal, needed to isolate an item from all others. Based on the number of lines needed for the isolation is considered an anomaly or not. The threshold here would be the number of lines or cuts used. So to say this is an anomaly, because these are isolated, this one has been left outside, but this is not because they've not yet been isolated by the cuts. It would take many more. If we were to choose this one here, and we would use random lines, we would need many more to isolate it compared to this other one. So we've already said, probably you cannot see that, but we've said it already that actually isolation forest is using decision-making forest. And how does it work? You get your data set, you get the features of that set. It looks into the features following some scores and metrics. This would be the GIN score, which is another score. And I will get this value and I will split it following this feature and value. This is on this one side and then the other side, and this is branch, another branch, and all the way up to the absolute purity in one branch. That is would be a pure spot. This is a classification algorithm that is supervised. So you need to know what's legit and what's not to keep assessing it. So, sorry, it's unsupervised because it does calculate the GIN score based on the cluster density and everything else as we were doing. So what does it do? It builds decision trees based on our set of data or data set. And so it will think that the cats here, so what we represented as cats, well, you see, these are actually separations from our data set, and so it becomes subsets. So we have the data set split into two subsets. We have this one here and this one here. Translated into a decision tree, we would have two branches, one here with this data. With another cat, actually, we have translated it into having a cat on previous cats, and so we have more branches created. What this algorithm identifies as anomalies are those sets that have a lower depth or a fewer branches all the way up to purity, and that's why it is tree-based. How can we follow this kind of algorithms on a real example for anomaly detection on a network? We can use our network, our local network, small one, at home, wherever. Use a tab between the router and the devices, or use a switch through VROI and redirect all the traffic on the internet on a machine where this algorithm is run real time, and see whether the traffic sets are anomalies or not. We will not do it package by package because it would be pointless, but maybe some flows, traffic flows with 10,000 network packages or sessions or login sessions, that is, and we can group them anywhere and any way we like. We can have net flow standards, that stats, and many other mechanisms. So all the traffic in and out of the network, we can check and see when there can be some anomaly on the network, our network. So the mechanism I have not deployed real time, but I got here a set of data. So I've got a data set here, which is already ready with some features of several network flows, and it's classified as well. Here we see this flow here, which is a regular one. You see it says normal, regular, and then the features I got here would be, let's see, incoming or outgoing items, many more things. TCP passive open, outgoing requests from TCP. So many features and different flows for the network traffic. You just get it, pass it, as we did with the emails. You get the features out, you dump them into your data set, and this is offline. But online, you would get the flow and send it into our system real time, and it would give us the odds that it is an anomaly or that it isn't. Isolation forest is easily implemented as well. See here, I've used a feature selection algorithm priorly, which do what we've done with the Gaussian distribution. See what the best distribution is, but here it follows some statistical mathematical methods. So this one is the one with the best results usually. And I kept these ones, so we change our isolation forest algorithm, same as we did before, and here we have it implemented, and we fit it into our data set. And the result are some scores. So here I'm detecting brute forcing on a web app. I have it on the network, and these are easily detected because you have someone trying user, password, and everything. So this is very different from regular queries and requests. And those flows, if I choose those flows, so if it's a 5-minute flow, that flow where there's some brute forcing, this is different from what's normal because it might be 1 per minute or even less than that. So here I find that there's brute forcing on my network, and for my set of data I had some 200 or 1,000 items or lines, but then I split the data set into 800 for verification and 200 for later purposes. And then F1 score, that is the score or metrics, that will give us the percentage of, yes, the percentage that is, for the proper classification of anomalies that were malicious examples and anomalies that were false positive, that were legit examples, that is a 92%. Which means that 92% of all the flows that have been considered abnormal were matched to flows that came from brute forcing. So that was it. So we've actually seen that there was an abnormal behavior. So we need to keep it real time, all well profiled. And when we do see that there are some real abnormalities, we need to suspect that there's something going on. And so you get the flows, you get the network traffic, you redirect it elsewhere to a different system. And so we have other mechanisms for machine learning and reclassification, or all based on malware, ransomware, for example, that is distributed on the network. It will be easily classified, or also brute forcing, or denial of service, or RPS spoofing attacks, or all those attacks that actually, if we go into it, we'll be able to classify it by properly selecting features. But if we use a classifier just on a large network where we've got plenty of data, we will get many of false positive. If we detect anomalies, we move that elsewhere, we can classify it, and the results are way better. That's been all for me, folks. Thank you very much for your attendance. I hope I did not bore you with my lecture and formulae and everything else. And so I have 10 minutes left for questions as requested. If you want examples or anything of this kind, or advanced questions, you can ask me on Twitter or in my email. Thank you very much.
Gracias. En el ejemplo que has puesto del...
You gave us an example for isolation forest, and you said that was about isolating a node, right? That's when it just stopped. No, there is decision-making trees, and it would consider an anomaly is what follows a depth that is shorter. So when does it stop building the trees? It depends. You can indicate it, maybe when the node is pure, so you only have one kind of an example, or else, so you might have a data set with lots of types. It would be a huge tree, huge and unmanageable tree. So you can say, I don't need the data set or node to be pure, but I need it to have an 80% purity. So when it says that through a series of techniques, such as the silhouette coefficient using Gini score, and it says that the cluster is pure enough, it stops and stops producing any more branches. Anomalies, since they are very much different from everything else, are isolated first, because that's the difference. That's it. When we said isolation forest, there were two premises. First, the abnormal subset has to be minority, and then they are very different compared to ordinary data. And so they're isolated in just a few branches, all right? But graphically, those are the cuts that we follow. Because right there, on your card, the second one is more than enough, right? That's right. That's what I didn't follow. Yes, here, the second one would have been enough for isolation purposes, but usually it would take on and on. If this were a tree, we would keep with cuts all the way to the end to see what's significant, because maybe out here it would work. Any more questions?
¿Qué suele ser más difícil?
What's more difficult for machine learning? Information classification or choosing an algorithm to tackle a problem? Well, the most complicated part of it would be to get a good data set, good quality. Getting a good data set, it is so very complicated. For example, you want to use isolation forest. It could be done, For example, to detect anomalies on a corporate network. So what about your home? How do you get data? Because you don't have access to a business network, and at home with a virtual environment you cannot have same traffic as on a corporation, because they have priorities and they have more nodes and hubs and have different structures within the network. So in the end, the problem is that you don't know whether you got a good model, whether it will be implemented, because you don't have access to information data to test your algorithm. So if I were to say something, I would say the most critical thing would be to get good data. And there are many researchers in artificial intelligence think that artificial intelligence has been a hit for the last 10 years, because before that we could not get good data. There were no mechanisms for good data collection, and we hadn't had enough time to have big enough data or good enough data. Now everything is faster and it's all expedited, and it's easier to get larger volumes than in the past. That's why I say that data are critical now.
¿Alguna cosa más? Pues si no hay más preguntas.
If there are no more questions, that's been all. Thank you very much.